sometimes the page table of a process is not available in the TLB. That scenario is called TLB Miss. Hey guys, what's up? I hope you're doing great. In this video I'll be telling you about how the operating system manages the main memory. These will be core concepts, very important concepts. Before moving on, please make sure you subscribe to my channel and you've hit the bell icon for notifications. Now, the main topic which is used most frequently in modern operating systems is called paging. Paging is a very simple memory management scheme in which what we do is we simply divide the complete memory for ease of addressing in two parts, right? So for example, I had a memory whose size was 512. So if I half it, it will convert two partitions. One would be called 256. One will have size 256, the other will also have size 256. And if I half it again, it will be the sizes of these four things will be 128, 128, 128 and 128. So we call these pages, right? So there are now in this memory there are 4 pages, and in particular if we divide the physical memory, which is the RAM, these partitions are called frames. One of the key property of these partitions is that these partitions are of the same size. They cannot have different size inside the same partition of memory in which this particular paging scheme is used. So then you would be thinking, why we call it paging if these are frames? The thing is, as I explained in the logical and physical address spacing, the same partition in the physical memory is called frames, right? In the logical address space where we have different programs, this is called pages, right? So for example, I have partitions 128 size, 128, 128, 128. So I have like so many different partitions or frames, each of 128 size. So what I will be doing, I will be in the logical space, I will be partitioning the processes into pages of size 128, right? So in logical space these partitions will be called pages, in physical space these partitions will be called frames. But obviously in the logical space the size should be 128, but there's a problem. 2 frames would always be size of 128 plus 128, which is 256. But in the logical space, a program does not follow any sizing. When you compile a program, the compiler doesn't think about what kind of page size you're going to put the program into. It simply compiles the program to the minimum possible optimized size it sees, and that's the best option, right? So for example, our program size was, let's suppose, 200, right? So let me draw it here again. So for example, this was our program. Let's say the name is again process 2, and and the complete size was 200. So what will I be doing? I will first start from the logical address 0 and I will be going up to address number 127, and I will declare that this is my first page, right? This is page number 1. When I go to the next address, which is 128, I will have to start the next page, which is page number 2. But the problem is the size of this process is 200. It is not 256. So the size of this page will be smaller. But the thing is, frames cannot have different sizes. Frames always have the same size. So for example, I have sent page 1 to some frame and I have sent page 2 to some other frame. Page 1 will occupy the complete frame, obviously, because page 1 size is 128. It will completely occupy this frame. But page number 2, it reaches a point of 200 and it ends, right? So this is the occupied frame of page number 2. But this thing is now free. This is free. This page by the way is called internal fragmentation. This is something we have to live with. We don't mind it too much because it is something that comes with the facility of having paging scheme. Paging is a really handy scheme because it's very easy to address different pages, but at the same time we get internal fragmentation. we cannot really do much with the problem of internal fragmentation just by adjusting the page size, but page sizes are normally fixed. When you design the operating system, you can have multiple page sizes but for different sections of memory, but you cannot have you cannot vary the page size on the go, that you can change just to reduce internal fragmentation. That is actually against the idea of paging, because you started with the concept that we will design a memory which will have fixed partitions and there will be no problem of addressing. So that was the concept of paging. Every address which is now generated will have a page number concatenated with the offset. So to explain this thing, you need to simply see that for example there are two pages in a process. Now when you want to read a location in memory, you're going to tell two things. You're going to tell which page, and inside the page how many further down from the starting of that page. That is called offset. This question mark, the starting address, is called page number, and the offset from the starting point of this location is called offset. So every address consists of these two parts. So that is the addressing scheme. Then quickly we look at paging hardware. Paging hardware is something which translates the address generated by a process into a physical address. The address generated by a process will be in this case logical address, and our paging hardware will translate the address into physical address. How it does that? It uses something called a page table. A page table is a data structure, you can say. It is a data structure which is an array of frame numbers which is allocated to each process. Whenever a process is created, it is obviously created in the physical memory, it is stored in the physical memory. So every page in the process is given a frame number where the page is actually residing in the physical memory. So let me show you an example here first. So this was our logical memory in which a process had 4 pages. Simple, right? There is a physical memory. It has so many frames. The frames can be as many as as big the physical memory is. Now page 0 is stored at frame number 1. So you can see that in page table. In page table, in first line which represents page 0, we have written 1, which is what? The frame number of the location where page 0 is stored, in which the frame number where the page 0 is stored. Similarly, let's look at just another one. Page number 3 is the 4th page, represents page number 3 of the page table. So that 4th row of the page table contains 7, which is the frame number of the location of the frame where page number 3 is actually stored. So that was the method of using page tables. Now coming back to this thing again. Now you get the idea what you've gotten the idea what page table is. The CPU, the process, is going to generate an address in the CPU which will be the page number and the displacement or the offset. So process the page number is in the logical space, so the operating system goes to the page table. By the way, you must remember that the page tables are also stored in the physical memory somewhere in the space of the operating system, right? So the operating system translates or checks to see, like for example, the operating system would the program would generate address of page number 2. The operating system will go to the page table and see in this area what frame number is stored in front of this page number. That would be the frame number. Then it can go physically to this frame number. So this is exactly what's happening here. So page number is being translated to the frame number, and the page number is simply replaced by the frame number here, and displacement is kept the same because the same displacement is used in the page and the frame. So this is quite a simple technique, and this is quite fast technique as well. Why? Because we are simply erasing this page number and we are instead writing frame number instead of that, right? So this is a paging example in which you can see that you have logical memory of a program. It has 16 different memory locations and only 4 pages. So there is page number 1, page number 2, page number 3, page number 4. These are actual logical addresses which are shown here, and similarly this is the physical space in which you can see that for example ABCD. Let's locate where ABCD is. ABCD is here. So this is the page which was page number 0. It is located at this address. This is the physical address, by the way, but the frame number is 5. What is happening at frame number 5 multiplied by the size of frame, which is 4, we are getting the physical address, which is 20, right? So there is something which may be missing in this picture, and that is the frame numbers. The frame numbers here are 0, 1, 2, 3, 4 and 5. This is frame number 5. That's why you can see frame number of 5 written over here, right? This is frame number 6 and this is frame number 7, right? And similarly this is page 0, this is page 1, this is page 2, this is page number 3. So this was again just a simple example to explain you further what paging is. You can also calculate the internal fragmentation. If for example you are given a page size, for example we had a scheme in which the page size or the frame size, which are same in all the cases, is 2048 bytes. The process size, the program size is 72,766 bytes. So you are interested in knowing that how many frames will be occupied by this process, each frame having this size 2048. What would you do? You will divide 72,766 by 2048. You will get something 35 point something something something, right? So you will say that this is approximately 36 frames, but 35 are fully occupied because you are getting the answer. The exact answer is 35.53. So you are saying that 35 frames are fully occupied, but there is another frame which will be used fully, but it won't be occupied fully by this process. And how much it will be occupied? You simply need to multiply 0.3 with 2048, this size, the size of the frame. So what do you get back? You get 1086. Sorry, this is 35.5. So you're going to multiply 0.5 with 2048 and you get 1086. As I said earlier that the page table is also stored inside the main memory, right? So how can the operating system locate that page table easily? Obviously every page table will be created by the operating system itself. So whenever the operating system will try to access, it will know, it will have in its own records the location for the page table for a particular process. But whenever a process is loaded into the CPU or context is switched to a new process, the operating system locates its page table's location inside the memory, which is indicated by these two things. First is called page table base register and the second one is called page table length register. So just like any other process, the page table, when it will go inside the memory, it will have two things associated with it. One is one will be the base address of that location and the second one will be the length of that page table, right? So both these things are brought by the operating system from its records into the CPU. These are registers inside the CPU. It becomes easy for the operating system to go to the page table to translate page numbers to frames because it will happen quite frequently, right? But the problem is, if we want to read an address or translate an address for the process, let's say this is the process, let's say process P2, and this is the page table, right? This is the page table. So just in order to go to another address, for example, this line in process 2 wanted to read this line, right? It looks really easy here, but the thing is the operating system will accept this request, receive this request, and it will go to the page table, translate the page number to frame number, then come back to the address of this process. So it is taking two memory reads just to get to one memory address. So in order to increase the speed of this, in order to optimize this, what we have done is that the modern computer CPUs, the modern microprocessors, have something that is called the translation leukocyte buffer. That's a small cache memory inside the CPU, which looks something like this. Its structure is just like a page table, although its translation leukocyte, its name is translation leukocyte buffer. And once you understand its function, you will understand the name is quite obvious, but for now you can see that the structure of this is similar to a page table, right? So here you have page numbers and frame numbers. So naturally it looks like something which is translating pages into frame numbers. So what we do is whenever a process, we context switch to a process, we bring the complete page table of that process inside the TLB, which is where? Inside the CPU. It is just drawn outside for illustrative purposes. So when the page table is readily available inside the CPU in the TLB memory, it's very easy for the operating system to read an address for a process. It does not need to go once to read the page table in main memory and then again go to the same address which it is trying to access. So it saves one memory read for that, and now it becomes one read for the TLB, which is much faster as compared to memory read of page table which is inside the CPU, inside the memory. So the process becomes much more fast, but there's a problem to this. Sometimes the page table of a process is not readily available in the TLB. That scenario is called TLB Miss, and TLB Miss means that the CPU, the operating system, tried to find the page table, but it missed and it went, then it needs to go to the main memory. This thing is drawn page table, but it is residing inside the main memory. So that is called a TLB miss. If the page table is found in TLB, that is called a TLB hit, right? So if there's a TLB hit, the page number is simply translated to frame number, and the page number is replaced by the frame number, and you get your physical address. But if that is not the case, once you go and try to find the page table in the TLB but you don't find it, so you go to the main memory. So you are doing extra work. So you read the memory, then you, just like before, translate the page number to frame number, and then you translate it to physical address. So this is what happens in TLB. You can calculate an effective access time for this, like so for example, alpha is defined as the hit ratio, right? For example, there is 100 times of trying to access an address, and out of that 100 there is 30%, 30 times out of 100 times you find the page table in the cache. That is called, then you will say that alpha is 0.3, right? So every time you hit, or the TLB is hit, how much time do you need to access a memory address? 1 times memory address, that is the actual data you're trying to access, and 1 time of reading the TLB. Similarly, if you miss, which will be the rate 1 minus alpha, in case alpha is 0.3, 1 minus alpha would be 0.7. How much time do you need? 2 memory accesses and 1 TLB access, because in case of TLB miss, you will still need to first go in the TLB to find out that it is a miss, and when you find out it's a miss, you again go to memory, read the page table, bring the page table into the TLB in parallel, and then you go to the actual memory address you're trying to read. So now there's an example, also a numerical example given here, that effective access time for a hit ratio of 80% and a memory read time of 100 and TLB read time of 20. Obviously 1 minus 0.8 will be 0.2, that will be the miss ratio, and 2 memory accesses will be, because one is memory read is 100, 2 will be 200. And again TLB was also read in this, so the effective access time for many reads, memory reads, would be 140 nanoseconds. So you can see that instead of 100 second, you're getting 140 nanosecond for a 80% hit ratio. That means TLB found the page table in it 80% of the time. still the effective access time is quite large. So even if the hit ratio becomes 99%, you are still getting an effective access time of 121 nanosecond, which is much bigger than 100 seconds. So it means that it's really effective access time is really driven by the hit ratio, and you need to seriously reduce the number of times the TLB is missed. Then we come to another subtopic, which is memory protection. Sometimes the page tables are stored, because obviously page tables will be stored in the pages themselves. So the page is will be stored in the frame, and frame has a fixed size. So sometimes there are left out locations in the page table. Page table is not driven by page size or table size, frame size. Page table page table depends on the size of the process, right? So for the unused page numbers, the operating system can mislead into thinking that these are also used. So in order to prevent that, we concatenate a bit, a single bit with this page table, which tells whether the page table is valid or it is invalid. And in case of virtual memory, it also tells us whether the page is inside the physical memory or not. So another subtopic, which is two-level page table scheme. Two-level page table scheme is where the page table becomes the number of page tables becomes so large that what we do is we create a page table of page tables, right? So there are so many page tables that we want to group multiple page tables and refer to all of them by one location. So this is called two-level page table scheme, and it can be extended to three-level paging scheme as well. So here you can see that at first the for two-level paging scheme, what happens is, first this is the displacement, this is the page number, this is the outer page number. So outer page number tells which page table, which group of page tables you are trying to get to, and out of those you select your page table, which is referred to by P2, and then you get to the displacement and get to the final address. Similarly, three-level paging scheme, first you tell the group of page tables which you are referring to, then you P2 here represents the group of page tables where you go to actual page table, which is P3, and then you go to your displacement, which is D. So this is three-level paging scheme. It is simply, it just makes the addressing a bit more convenient. So here you can see for Intel x86-64 architecture, you can see that they are using four-level paging technique. This is the offset for 12 bits, this is the offset for 12 to 20, this is the actual page table, and the group of page table in Intel x86-64 is known as page directory, and the further group of these are called page directory pointer table, and the further group of these is called a page map. So it allows for another thing, it allows for making page sizes of different sizes, pages of different sizes. So if you are simply using this offset, you are using 2 raised to the power 12, which is 4 kilobytes page size, right? But if you want to use all of this as an offset, which you can do here because you have partitioned everything, you will be using 21 bits for offset, which means you are using a page size of 2 megabytes. And if you use all of these three partitions as offset, you can define a new, because this is 29, this will be 2 raised to the power 30, which is 1 gigabyte of page size. So Intel x86-64 offers 3 different page sizes, and as we looked earlier, that internal fragmentation can be controlled using different page sizes. So the operating system can think about storing the process at different locations based on different page sizes. Or, by the way, this is hardware support for page sizes, so TLB will be supporting these page table sizes. Similarly, ARM architecture, it offers two-level paging scheme, outer page table, inner page table, and then offset. All of the sizes are mentioned here: 4 kilobyte, 16 kilobyte, and the outer page tables are called sections. There are 2 different sizes of sections, 1 megabyte and 16 megabytes. So this was briefly what how the operating system manages memory in your computer. I hope you understood everything. I hope you don't have any questions. If you have any questions, you can comment below. If you like the video, press like. If you haven't yet, please subscribe. Thanks for watching.